playing with you.
Cool. So this is the velocity. One way to. Alright, I just thought about the Velociraptor.
Isn't there a brand called
The
Velocity?
fastest.
Like a clothing brand called Velocity? Or a band called Velocity? Like Pac.
Yeah, I don't know about that one.
I've seen like Velocity or something. Like,
You ain't see that. You seen the lightning bolt. That's
no,
what you seen.
Velocity. No, it's Volcom. That's what it is. Volcom.
I heard of that.
It's etymology. Similar. Your notion of velocity is probably the same as its scientific definition. You know that if you have a large displacement in a small amount of time, you have a large velocity. And that velocity has units of distance divided by time, such as miles per hour or kilometers per hour. So this is where we were talking about average velocity is displacement change in position divided by the time of travel, where v, how would you say that? Where the average of v is the average indicated by the bar over the v velocity. Delta x is the change in position and displacement x f and x not final and beginning positions of t, respectively. Time is taken to be zero, then it's just that. Notice that this definition indicates that velocity is a vector because displacement is a vector. It has both magnitude and direction. The SI unit for velocity is meters per second, but many other units such as kilometer per hour, miles per hour, also written as mph, and centimeter per second are in common use. Suppose, for example, an airplane passenger took 5 seconds to move -4 meters, which means that it's going toward the back of the plane. His average velocity would be like this. The average of v equals delta x over t, which equals -4 meters over 5 seconds, a -0.8 meters per second. The minus sign indicates the average velocity is also toward the rear of the plane. The average velocity of an object does not tell us anything about what happens to it between the starting point and any point. However, for example, we cannot tell from average velocity whether the airplane passenger stops momentarily or backs up before he goes to the back of the plane. To get more details, we must consider small segments of the trip over smaller time intervals. XA, so he starts here, X0, XA, XB, XC, XD, X total.
Oh, and that's just the passenger walking back and forth?
Like, starting here, came, stopped, talked to somebody, went over there, looked at a seat.
I hate to be in his row.
Doesn't really like that seat, huh?
I would hate to be in his row.
Doesn't really like that seat. Let me go back. I saw a cute girl. Maybe I could sit there. Oh, let me go back to the back of the plane. I gotta use the restroom or something. So.
That's definitely not a real plane, though. Like, you have 2 engines. That's too small to have 2 engines like that.
You know what? It's just a part of the picture.
That's all I'm saying. That's not a real plane. Like, if you got 2 engines like that, 9 times out of 10 is like a 747. But that's like a 737 body. Yeah, 47. Yeah.
One book, do better. The smaller the time interval is considered in a motion, the more detailed the information. When we carry this process to its logical conclusion, we are left with an infinitesimally small interval. Over such an interval, the average velocity becomes the instantaneous velocity, or the velocity at a specific instant. A car speedometer, for example, shows the magnitude but not the direction of the instantaneous velocity of the car. Police give tickets based on instantaneous velocity, but when calculating how long it will take to get from one place to another on a road trip, you need to use average velocity. Instantaneous velocity is the average velocity at a specific instant in time or over an infinitesimally small time interval. Mathematically, finding instantaneous velocity v at a precise instant t can involve taking a limit calculus operation beyond the scope of this text. However, under many circumstances, we can find precise values for instantaneous velocity without calculus. Which brings us to speed. In everyday language, most people use the term speed and velocity interchangeably. In physics, however, they do not have the same meaning and they are distant concepts. One major difference is that speed has no direction. Thus, speed is a scalar. Just as we need to distinguish between instantaneous velocity and average velocity, we also need to distinguish between instantaneous speed and average speed. Instantaneous speed is the magnitude of instantaneous velocity. For example, suppose the airplane passenger at one instant had an instantaneous velocity of -3 meters per second, going to the rear of the plane. At that same time, his instantaneous speed is 3 meters per second. Or suppose that at one time during a shopping trip, your instantaneous velocity is 40 kilometers per hour due north. Your instantaneous speed at that instant would be 40 kilometers per hour. Same magnitude, but without a direction. Average speed, however, is very different from average velocity. Average speed is the distance traveled divided by elapsed time. Seems pretty similar. We have noted that distance traveled can be greater than the magnitude of displacement. Distance traveled can be greater than the magnitude of displacement. So average speed can be greater than average velocity, which is displacement divided by time. For example, if you drive to a store and return home in half an hour and your car's odometer shows the total distance traveled was 6 kilometers, then your average speed was 12 kilometers per hour. Your average velocity, however, was 0 because your displacement for the round trip is 0. Displacement is change in position and thus is 0 for a round trip. Thus, average speed is not simply the magnitude of average velocity. Interesting. So it says during a 30-minute round trip to the store, the total distance traveled is 6 kilometers. The average speed is 12 kilometers per hour. The displacement for the round trip is 0, since there was no net change in position. Thus, the average velocity is 0. Wow. Another way of visualizing the motion of an object is to use a graph. A plot of position or of velocity as a function of time can be very useful. For example, for this trip to the store, the position, velocity, and speed versus time graphs are displayed here. Note that these graphs depict a very simplified model of the trip. We are assuming that speed is constant during the trip, which is unrealistic given that we'll probably stop at the store. But for simplicity's sake, we will model it with no stops or changes in speed. We're also assuming that the route between the store and the house is a perfectly straight line. There's position, x, kilometers, well, position, kilometers, and then the amount of time that it took. So we start from 0, go 3 kilometers, and point a little over.
That's 2.5.
Yeah, point. Yeah, 0.25. And then to 0.5. Yep. Sounds good. But our velocity versus time graph is going to be a little different. Because our velocity, kilometer per hour, we were at.
Velocity is like how fast you're going, or?
My change in velocity is change in position over the change in time, which is, yes, basically how fast you're going. So and then we have velocity, so 12 kilometer per hour. And then at that 0.25 we stopped. I would have liked for them to put the velocity, I would have liked for them to put them starting at 0. They speed up to 12 kilometer per hour, and then we pretty much coast down the street at the same speed, but they just eliminated that part because you technically aren't able to just start at 12.
Right.
But we stopped, so my velocity 0 because I stopped, and there would be a time where you slow down because from 12 you're not just gonna slam on the brakes, So in a real world problem, this isn't exactly what it would look like. You would typically have boom, 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 and then go to 0. And then it would be doing it again. Boom, boom, boom. Anyway. And then our speed versus time. So 12 kilometer per hour. That's where we are. And so position versus time, velocity versus time, speed versus time on a trip. Note that the velocity for the return trip is negative. Making connections, take home investigation, getting a sense of speed. Well, that was pretty fast. Maybe we can go to acceleration. I think it'd be good too, so that way we're halfway done. Anyway, speed. If you have spent much time driving, you probably have a good sense of speeds between about 10 and 70 miles per hour. But what are these in meters per second? What do we mean when we say that something is moving at 10 meters per second? To get a better sense of what these values really mean, do some observations and calculations on your own. Calculate typical car speeds in meters per second. Estimate jogging and walking speed by timing yourself. Convert the measurements into both meters per second and mile per hour. Determine the speed of an ant, snail, or fallen leaf. Alright, cool. So calculate typical car speeds in meters per second. Yeah, so we typically have it in miles per hour. So in order to do this,
Let's see how many miles.
in a meter, yeah. One mile is 1609 meters. Alright, cool. Calculate typical car speeds in meters per second. So that was 1609.34. And 70 miles per hour. So what's a good wonder, would it make sense to do the problems over here? Seems like this is more the middle of the class. I don't know if they put these up recently or.
Ain't got no date on them? I don't know, you want to move them up?
Yeah, I kind of want
I know
to just move them over. I
I
started
broke
breaking.
it.
Yeah, I broke that one.
Oh. Yep. Don't want nothing to do with that one. Shoot, they all, I think they all.
Really over here. Like, yeah, to the right side.
Yeah. Hey.
This one on top of it. Muchas gracias. Right there. Oh, it's not right.
It's gonna stay Alright.
So we could do MPH to meters per second. So we should be able to do that. Which quantity do y'all want to do? Y'all want to do a lesser speed or a higher speed?
Let's do 25.
25. All right.
25 miles.
You said that's average?
It says
Yeah,
calculate
we're just-
typical car speed.
45.
I'm saying, but like
Well,
in the slow lane.
Yeah, in
The
like
slowest you'll
The
go.
slow lane of what?
The slowest you'll go. Like the low, 'cause when you go down those back roads, when you go down those back roads,
Oh.
they have you doing 25.
Okay.
No, that's still kind of fast for a back road, 25.
You know,
Okay. Yeah, really
Like
good.
15,
Really
15,
good.
20,
you know, this is a neighborhood.
Do 20.
This way you go. You worry about the wrong.
Neighborhood, and then a typical street. I don't know, typical street, and then we do highway. So that way we get the whole array. Yeah, 25, that's cool. And then I know I typically go about 40 miles per hour. You know, 35 is the speed limit. So let's do 35. I could do 25. I give us a little bit of a different from 35. But on the highway, I want to say
65, 70, 80,
Yeah.
90.
Yeah, let's do something that's let's do a number. You said 90.
Nah.
Thank you.
65.
Let's do
You
that.
know, that's always a typical number right there on the tank. 65.
Let's do something like
Come on the highway?
72.
Yeah, the number when you get, you know, you hitting the highway to the first fat, biggest
You do
number.
not
you
drive
hit.
65 on the damn highway.
I'm saying that's the number that's.
That's
That's the speed limit, but your bike was 65.
I know that. I'm gonna say it. 75, 80.
Yeah, 75.
It'd be like,
The
no,
lowest number
he
do-
writes 72, 73 is what people typically
Yeah.
in the slow lane.
What it is, the left lane,
The
the
right
right
lane.
lane. I don't know, my left and my right like that.
Dang.
I just be in the car.
Left or right, alligator hands.
Yeah, I don't know, I'm just not familiar with it.
So, anyone want to take a stab out of it?
I mean, I don't know what I'm doing. I'll try.
You always know the bottom number to start. So we need to see how many meters is, or actually we need to see how many meters is gonna go into a mile. Which he already found out.
Okay. Yeah, 1,600 meters is in a mile. Okay.
Yeah.
20 miles.
Okay. Okay, so 1,609 times. Wait, no.
Well, write it out. Write it out.
Go ahead.
Okay.
Oh, yeah, write it out. 'Cause
Alright, so. Wait, so would that be 1609.34 over hour?
No, that's 1 mile. We did
Oh, yeah, he already
mile
put that.
equal meters.
no, that's just for the mile. So So what is that? That's 1609.34. What unit is attached to that?
That's a mile.
Right.
I mean, but that's 1 meter.
Right. So
So you want
that
hours?
unit is meter over.
Yeah.
Either
1
way you
mile.
want to do it. You can start with go ahead and converting the miles into meters, or if you want to go ahead and convert
Alright.
the hour into how many
Which is-
seconds you want to get.
Yeah.
It just depends on what you want to do.
All right.
No.
No.
Just wait. Just put.
You want me to do it?
Just focus on meter. So the 1609.34.
Mhm.
What's the unit attached to that?
Meter.
Meter. So put meter,
Mhm.
and then divided by this 1 mile. This is 1 mile.
Mile, right.
Yeah. So let's put 1 mile at the bottom.
And you always gotta cancel out stuff. So the next thing to go on top times it, and you gotta do mile on top. So what mile are you working with? 20 miles. And you start that.
Yeah.
So times 20
So-
miles.
So now, I typically just, so you could do 20 times that, and then we'll know what it is, meters per hour, and then we can do.
You mean 20 times 1 mile?
No.
Or 20 times 1609?
Yeah, 1609.
Yeah, you're trying to figure out how many meters are in those 20 miles. And then afterwards, we're gonna convert the hour to see how many seconds that is, and then you're gonna
Check out the
multiply
door.
the seconds with
Yeah,
or divide. Yeah, you're gonna multiply.
20 times 1609.34 is 32,186.8. So I'll get this out here.
You can put it over there.
Yeah, you could say equals
That equals 32,000.
186.8. Okay.
Right.
So what's gonna be our units here?
That is, that's miles,
No,
right?
these are the meters.
Go ahead and
No.
cancel out first.
Cancel.
Cancel out this. So we did 20 miles per hour,
Yeah.
and then we multiplied by 1609 by this.
Mhm.
So what will we cancel out? How do we cancel
Because you're trying to get
out?
hours, right? Well, no.
You moving too fast.
Right, so- I think
Put the X
so
right there.
this-
Put the X.
we would cancel out mile to mile.
You missed it. Put the multiplication X in the middle so you can see what you're looking at. And since we cross multiply, you need the X out mile and mile. Those cancel out. Put a slash across them so you know what you're seeing. Thank you. So you no longer have miles. You have meters.
So what's left?
Meters over 1 hour. That's all you got left. So that's meters
So we'll
up
put that
there
over here. Meters.
over the hour. Yup.
Yeah, that's what I was saying. That's what I was saying.
I was saying it very much.
That's what I was saying. Over an hour, right? That's what I said.
Now you need to change your hour to seconds.
That's why I put 60 seconds.
You can't
No.
do
gotta
that
do step by
first.
step.
That's what I'm saying. You keep skipping steps. Your mind is moving somewhere, but
I mean-
you ain't writing it down.
Yeah, because
Okay.
the reason why
You
we
just like, oh well, let me get this big number and then time it by 60
Well,
seconds.
well,
That's not how many
keep
seconds
that.
it is.
Keep that. Do
Another
keep
big
that
number.
hour right there. Keep
Okay.
that H right there. Cause and then we'll come over here. We'll do multiply. We'll do
60
another
minutes.
X. Right. So now we needed to see hours to minutes and then minutes to seconds.
seconds.
Cause that'll be a lot easier.
Really?
And you got 60. Yeah, you just trying to do time 60. That's not enough.
Oh, okay. You ain't got to throw me under the bus.
No, I got to, 'cause I need you to get it through.
Okay.
Alright, so
That's not enough.
now we're saying, so we want to cross out H, right?
Right.
So where do we need to put that
we need
hour
minutes. We
on
need-
the top? Right.
Okay,
so we want to get minutes, but in order to cross out hours, we will have to put that on the top. So we'll say 1 hour up here, and then
60.
divided by, we're trying to get minutes. So let's look at minutes. How many minutes is 1 hour?
60 minutes is an hour.
Yeah,
Correct.
go ahead.
Yeah, so put 60,
Yeah.
60 minutes.
And then you need to go ahead
Yeah.
and get you need to cross out that hour and then go ahead and multiply for them seconds.
Mm-hmm.
So go ahead and put you another cute little X
So now, yeah.
and do 60 seconds over a minute. Oh no, a minute over 60 seconds.
Yeah. Because you want to cross out 60
Yeah,
minutes.
you want
and
to
that's
get
on
across
the
the
bottom.
pot. I mean, as you go, you're going to know that it's automatically going to be the 3,600 every time.
True.
Like, if you just, go ahead. You got it. Put your little minute over 60 seconds. 160, come on. You keep thinking about it.
Because I feel like, I guess my head feels like I'm moving too slow.
Huh?
Like I'm
Oh,
kind
you
of,
moving
I'm kind of
too
dumbing
slow.
it down. Like,
You
and it's,
moving too slow, huh? But you was just gonna skip straight to 60.
okay. All right. So, I got my meters.
Yeah, let's send it to the side for now.
Okay. Okay.
Like, you're not
okay. So I ain't worried about
messing
that no more right now.
Yeah, that's
now.
your
Okay,
big number.
so-
You need 2 big numbers.
Okay. So I need second. I know I need seconds.
Mm-hmm.
So 1 minute.
So 1 minute,
Mm-hmm.
and then
Put the unit with that too.
Yeah, because you always need to know what you crossing out. You're going to cross
Yeah.
out whatever
1
on the
minute
bottom.
and, 60 seconds is in a
Correct.
minute.
Yep.
60 seconds. is in a
Okay.
minute.
So now cross out. Yep. Alright, so now we can say equals. So now we're at what we want. We crossed out everything, we got meters and seconds. So now we just need to do what we just did. 32,186. You don't have to write anything at the moment. But
No, I was just gonna,
Yeah,
Just
I
for-
see what you mean.
just for shits and giggles. I mean giggles.
86.8 divided by
Oh, I can't.
divided by another 60. So I get 8.94.
8.94.
Right.
And what we got left right now? We got 8.94. What is this? That's for the meters over second.
Yeah, that makes sense.
What you multiply this with? The 3,600 right now.
60.
Left with a bigger number.
Yeah, we should.
Yeah, that's what I'm like. That number 8.9. I'm like, that's not.
That's all in the speed drop.
I'm saying, so what you did you do the 32,000?
32,186.8 divided by 60.
I thought it was,
No.
I thought it was in time.
It's times 3,600. Right?
Yeah.
It's times 3,600. So you can, it's gonna make the numbers, hold on.
No,
But
we
now I gotta
still have
type it
to-
in.
We still have to.
But yeah, something like to be
We
divided.
still have to keep it on the bottom.
The way y'all wrote it out that's how y'all getting confused by it. The way you wrote it out.
What you wrote? Yeah, right.
So how I do it,
Yeah.
that hour, I put 60 minutes over an hour. So I keep everything that I'm supposed to multiply on the top instead of putting it on the bottom.
It gotta be, but that's just
Yeah.
basic form, that's just basic standard formula, like how it's supposed to go, you gotta. Cause if you was to just do everything across, like how you usually do.
I think
for
this is
regular-
correct because you gotta take into account that's 20 miles per hour.
How many? But yeah, you know
And
what?
we're talking
I was
about
thinking about that.
per second. So
Okay,
so
so
we
would it be-
did everything
Oh, and
that
that's how many.
we're doing everything
So you
correct.
guys divided by 60 seconds.
Right,
Yeah,
we
years per
have to
second.
divide 60, well, first we have to divide by the 60 minutes and we also have to divide by the 60 seconds.
Oh, so
'Cause
did
if-
you divide by 36?
Correct. We have to
100?
divide by 3,600. Correct.
Oh,
Divide
okay.
by-
2,186.
Wait, that's what you
That's
said.
cool, that's cool.
3,600 is 60,
60 minutes.
60
60
times